Saxon Algebra 1, Lesson 64. Before we begin with that really fascinating definition I've laid out there before you, in the video chat this week, my friend Jackson, I will have you do 2 review problems, one for last week and then one for this week. I just wanted to mention that to you before I forgot, so that you'll be mentally prepared to deal with 2 problems instead of just one when we chat on Fridays, when I usually chat with you. All right, so remind me if I forget. Teacher, don't forget to make me do twice as much work. Oh, okay, thanks for reminding me. About this. All right, this is a really boring mathy definition. A domain is a set of permissible replacement values. Now, let me give you a real life example that will help to illustrate. I don't know about your mom, but around here, where I'm the mom and not just the math guru, I wear many hats, you guys. Very often I will say to my husband and my 2 daughters who still live at home, I will say, hey, what would you like to have for dinner tonight or tomorrow night? And no one ever says to me, let's have Lucky Charms for dinner. No one ever says to me, let's have ice cream. Not for dinner. No one ever says to me, let's have fried camel tongue. No one ever says to me, let's have locusts. There's a reason why. That's because these are not foods that we consider to be appropriate dinner food. All right, Lucky Charms and ice cream are lovely. They have their virtues, but they're not something that in our family we would have for dinner. They're not in the set of permissible replacement values for our dinner menu, okay? What we would choose from is something like, spaghetti, or we have a lot of stir fry. Every Friday we have pizza. Pizza party Friday night, you better believe it. What did we have tonight? Oh, we have a lot of super stews. Okay? These are what we consider to be within the domain of our dinner menu. They are permissible replacement values when I ask the question, what should we have for dinner? I bet your family works much the same way. So domain is like what you're allowed to choose from when your mom asks, what do you want for dinner? These are not in our domain, all right? Because we don't eat these for dinner. Fried camel tongue and locusts, we don't eat at all. These we use sometimes, we eat these sometimes, just not for dinner. Okay. So, how does this work in an actual problem, teacher? Why are you just talking about weird dinner items? We're going to be given a problem that looks like this. We're told to graph x is greater than 2, but then we have something weird afterwards. There's a comma and then an uppercase D, parentheses, and then it says, and I'm going to have to write it on 2 lines because I ran out of space. It says real numbers. What this means is that our domain for this problem are the real numbers. And when we write our answer, we want to show all of the permissible values within that set. Okay, now we have to think back to that chart we made last time. Which ones are the real numbers? Look, I can show you. One of the beauties of working in a book rather than on a whiteboard. Remember this whole thing that we did? The real numbers are everything, right? So what that means when we are drawing the graph of this is the number line. X is greater than 2. I'm just going to put the 2 in. I'm not going to put anything else in. X is greater than 2. That means it doesn't include 2. So I draw the circle to say everything but 2 exactly. And then I draw just a solid line like this. And what this says, this is the way that we indicate the real numbers, because I'm saying that every single little number. I'll draw these in just to help your imagination. All the tiny little fractions and decimal numbers that are hiding in between these whole numbers, all of those are part of the answer because our domain is real numbers. Does that make sense? Let me contrast it with the next one. This time we're also told to graph, and this is x is not greater than or equal to 3, but this time our domain equals the integers. Oh, okay, well that's different. We'll look at that in a minute. Let's fix this. If x is not greater than or equal to 3, then we know that x is less than 3. And let's just take a look at that chart again. Come back to me, little Sheba. Let's remember what integers are. Integers are, okay, they're whole numbers, which includes 0, and then also the negative. So they're positive and negative whole numbers. All right. So that means when we're graphing, we have to be more careful. We can't include all the little pieces in between. So let me just do this. 3, 2, 1, 0, -1. This is kind of random, which numbers you put on and which numbers you don't bother to put on a number line. I'll talk more about that as we go because I don't want you wasting a lot of time drawing a highly detailed number line for these problems. For right now, I'm putting in a little more detail just because we're beginning and I want you to understand. We want the values for x that are less than 3 that are also integers. We can't include 3 because there's no equal to there. So 3 is not an option. 2 is the first integer that fits our inequality here. So we can only dot the ones that go smaller, right? We can't just draw the whole line. We can't include 3. This is our solution. Oh, that's weird looking, isn't it? But our domain was integers. The permissible replacement values are only the integers. We cannot use all the real numbers. So that's why we can't draw the arrow, and we have to make the dotty dots. All right. Let's see what else I can dream up to torture you with. 64.3. How many of these are there? 5? Yeah. And then we have a couple more that illustrate another topic. I mean, it's a party. Graph x is greater than or equal to -1. Domain equals the reals. I will eventually start abbreviating over here. I want you to write this down when you write this down in your homework. Because I'll tell you why. I have a really good reason. Because if you just glance at it in the book, you don't remember. If you write it down using abbreviations, you'll be fine. Okay, x is greater than or equal to -1. So I put that prominently. Throw in a few more. Throw another one in that direction. We want the values of x that are greater than or equal to -1, and it's the reals. That means we don't have to make those dots like we did last time. The real means all the little bitty numbers in between. So I circle this, and I draw the arrow going this way. That's our answer. Ready for a miniature trick? Graph. All right, we're supposed to fill in all the values for x that are less than -1, but are also positive integers. Well, wait a minute. The numbers that are less, let me just draw a picture so you can see this. Here's -1. We're supposed to be doing values for x that are less than -1. Well, if we chose integers, that would be like -2, -3. But our answer, our domain limits us to positive integers only. There aren't any positive integers that make this true because they have to be less than -1. So guess what? Three ways of saying the same thing. There's no answer for this. This we call the null set. This we call the empty set. Because there are no values that can make both of those things true. Or you can just write no solution. That's always kind of a fair way to say it. All right, but I'm a fan of the null set and the empty set. So sometimes these problems are tricks, and given the domain, there are no values that are going to make that work. One more of these. It's not a trick, I'll tell you that right now. X is greater than or equal to minus 5. Now that you've got the hang of this, when you write the domain, I want you to write that much. That's really fast. Now you can start abbreviating what goes in here. This time it's also positive integers, so I'm just going to write like that. You don't have to write it all out. For the reals, I just put an R in, okay? And honestly, in most of these problems, it's either the reals or the integers. This positive integer thing, we're not going to do that forever. So abbreviate it, but write something. And just make a little squiggle for those parentheses. They don't have to be perfect. All right, here's our number line. We know that -5 is important, so I'm going to put that like there. -6. All right, we want values of x that are greater than -5, but are also positive integers. Oh, okay. I'm going to have to make my number line bigger. And P.S., it's perfectly fine to do that. Like, I drew it and it was too big, so just add on to it. It's fine. Okay, we can only have positive integers. We would start here, right, and put dots on all of these. Integers means dots, right? But we can't include these negative numbers. And 0 is not a positive integer, so we can only start making our dots right here. Okay? Now, one thing that most students hate about the integers is that there's no way to show that they keep going. Our arrow for the real numbers is really nice because we can put an arrowhead on it and it means just keep going. And here, there's no such satisfying way to show that the dots continue. We've just learned to accept that, and it's okay. This is the right answer, and that's correct. Don't feel bad about the fact that there's no way to show that the dots keep going. It's okay. It's all right. Okay, let's up the ante on these problems just a wee bit more. I promise you this isn't hard. Take a look at this. We're supposed to graph this. And I'm going to start using the abbreviations too. So that stands for the reals, okay? Now look what's going on over here. We have not just a straightforward little inequality. We have this weird 2 clinging on to the x. Do you know what we have to do? We have to swim that 2 to the other side of the inequality, just like we would if this were an equal sign. The fact that it is an inequality does not bother us. We can add and subtract across that just the way we do across an equal sign. So I want to subtract the 2 because I want that to cancel. X is less than -2. Okay, now that's graphable. Domain equals the reals. So we know that with the reals, we're either going to have a circle or we're going to have a dot. This is when we're having greater than. This is when we have greater than or equal to. Right? Those are our two choices for the reals. Right? Reals are always an arrow. Greater than, we circle the number and go up. Greater than or equal to, we put a solid dot. Obviously, if they're less than, it's the same distinction. It's just the arrow goes in the other direction. All right, so now what we want to do is we want to say x is less than -2. So here's what I'm going to do. -2 is the only number we need. It does not an equals to sign, so I know I need the open circle. And then my arrow goes that way. That's my final answer. And that is correct. It's very important that you understand when to use the open circle and when to use the closed dot. okay? So make sure you understand the difference there, okay? But what we're learning in this problem is that we can swim things in these inequalities, and it's fine. 7. Domain equals the integers. I usually just write int. Okay. Same problem. X is not by himself. We can add and subtract. It's fine. So we'll add 3 just as we would if it was an equal sign. X is greater than or equal to, that's minus 2. All right. So I always do that first. I clean this up. And remember, I want you to do it exactly the way I do it. So first we clean up the algebra. We get a graphable equation. Then we go look at our domain. This is integers. Now let's do a little thing like this for integers. If it's greater than, then what we do is we don't put a dot on the first one. We start on the next one. And if it's equal to, then we start on the first one. Okay? So this picture shows us the 2 choices for graphing when we're graphing the integers. I call these dots, and I call these arrows. So arrows always reflect the real numbers. These dots always reflect the integers, okay? All right, so this one we're doing integers. That means we're going to be doing the dots. Either we include the number if there's an equal sign, or we don't include it if it's without an equal sign. This one has it. And when we're doing the integers, we have to write a little bit more. If we're doing the reals, you can just write the number in the expression. For these, we have to show a little more. So here's what we're going to do. We're going to put minus 3, minus 2. Okay, greater than or equal to minus 2, that means we want to include the number, and then we go up from there. And again, even though it goes to infinity, we don't worry about showing that. All right, and guess what? We're done. I'm sorry. I don't have any more problems for you. That's so sad. Make sure you understand this really clearly. Again, if it's less than, it just is in the opposite direction. But when we only have greater than or less than, we do not include the number in the expression. If there's an equal sign like this one, then we can include it in the graph. All right, so this helps you generalize the rules. All right, 64 is done. Yay! Congratulations. Another week comes to a close. I will see you different days for you, but I'll see you on the chat. Farewell, students.